Hello class, this is Ms. Friggins with today's video on section 8.4, trigonometric equations and inverse functions. As you're watching the video, please remember to write down notes including important information, equations, statements, formulas, examples, and graphs. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what's going on in the video. And at the conclusion of watching the video, write down a brief summary about what occurred in the video in your notes and submit that summary as well as an top question via the online whisk form. All right, let's begin. Today's topic is going to be similar. It's not going to be that difficult because it's a review of some things that you already know how to do. We already know about trigonometric functions. We already know about inverse functions, and we're going to use them to solve equations. So, of course, there are multiple ways to solve or strategies to solve equations, whether they're trigonometric or not. Graphically, numerically, analytically are the main strategies. So let's take a look at graphically. Let's say someone wants us to solve this equation. What value of t will make this statement true? Well, graphically means that all I can do, I can graph each side of the equation. So I would graph over here in blue is negative 5,000 cosine pi over 6t plus 10,000. And in the vertical line, the horizontal line is y equals 12,000. And to find out where they're equal or where we're finding out the points where they intersect and the x values that make that occur could be identified approximately around these values. Now, normally, if you have a graph, you can't get necessarily that degree of accuracy because our eyes just aren't that good to the 1,000. But you do get an idea of where the solutions will exist on the x-axis, as you can see. And so the graphing method is a strategy that will give you a quick answer, but the answer may not be as exact as you would like it. Another way to solve this is algebraically or analytically, where we actually get the t value by itself by doing algebraic operations. So as you all know, we could subtract 10,000 from both sides. Then we can divide both sides by negative 5,000. And then we can end up with a cosine value, and we can take the inverse cosine or the arc cosine to get what pi over 6 times t is. And then we can solve for t by multiplying by 6 over pi, and we get an approximate answer, a more exact answer as well, depending on how exact the answer from the arc cosine. Another issue you may see is that using this method, we only get one solution, whereas if we use the graphing method, there's two solutions. Why is that the case? Well, if you recall, the arc cosine has a range of only values between 0 and pi is around 3.14. And so therefore it would not include a value of pi over 6 times t where this value is it's greater than 3.14. So as a result, we don't get the answer to include the 8.214 because the arc cosine doesn't give values for the angle that's above, that's outside of its range value. Domain value. Okay. So again, even though this method may be more exact, it doesn't give you all the solutions. It may only give you the solutions that are within the domain of the arc cosine or arc, whatever the trigonometric function. So the question is, how can we be sure of a strategy that will give us all the answers and as exactly as we need it? And that answer is a combination of both of those strategies, graphically and equations. So let's take a look back at the original problem. Let's say we do graph the solution, the equations, the left side equation and then the right side equation. And as you can see, we are going to have two solutions. But what's the relationship between the solutions? Well, because we're talking about cosine, which is symmetric in certain senses, in this case it's symmetric about 6, then we know that the answer, both answers differ by a value of 12. So in order to get one answer, the second answer, we can subtract from 12 that answer and get that value, okay, as we see right there. Okay, moving on. I want to talk about the inverse cosine function. As we know here, we already said earlier that the inverse cosine only works for angles that are between 0 and pi, whose cosine is y, and y value is between -1 and 1. Okay, so that's important to note. So in this case, as you can see here, if you recall, that we're only taking a look at this portion of the graph from 0 to pi for our arc cosine, and so therefore we only are looking at these x values from 0 to pi. Sorry, these y values from 0 to pi. Okay. Quick question. Someone had asked me a few videos ago, why do we call it arc cosine? And I said I didn't know, but then I found out why they call it arc cosine. The output of arc cosine is an angle whose measurement is the measure of the angle as well as a measure of the arc that's produced by that angle. So they call it, instead of the cosine that gives you out a ratio, the arc cosine gives you out the length of the arc. So arc sine gives you the length of the arc that's produced by the angle of that length, and same thing for arc tangent. Okay, just wanted to follow up. Now, another way we can solve trigonometric equations besides graphically and algebraically is by using the unit circle. And if you recall, if I want to ask, well, what's the sine, what angle produces a sine theta of 0.9063? Well, I can use the arc sine, but using the arc sine, I will only get out one answer, and that answer will be in the where the angle is between -pi/2 and pi/2, or -90 and 90 degrees, as you can see here. But there's actually more than one answer on one rotation of the unit circle, but this second answer is outside of the -90 degrees to 90 degrees range that the arc sine will give me. So if I'm going to figure out all the answers that have a sine value of 0.9063, I can use the unit circle. Using the unit circle, I'm looking for another angle that produces 65 degrees with the x-axis, but this time in the second quadrant. And I can find that angle by basically taking 180 degrees and subtracting 65, and I get 115, okay, degrees. And as you can see, this angle right here is 115 degrees. And if I were to put into my calculator the sine of 115 degrees, it would give me out 0.9063. Okay, so I know that just from 0 to pi, I only have two solutions. And in fact, from 0 to 360, I only have these exact two solutions, which are 65 and 115. But what if my domain, my theta value, can go beyond 0 to 360? What if they can go on from, let's say, -360 to 1080? How do I figure out that one? Well, really, that basically means I need to go around the circle more than once and in another direction. And so how do I do that without manually trying to do that? The easy way is algebraically. So if I'm at 65 degrees, then one time around the circle is going to be, and back at this point will be 360 added to that 65 degrees, so I'll get 425. I wrap around the circle a second time, which is another 360 degrees, so I add to 425, 360, and I get 785. Or I can take the equation 65 plus 2 times 360 and get a second, get 785 as well too. If I go 3 times around the circle, 785 plus 360 will be outside of my 1080 range, so I can stop after 2 times around the circle. Since I'm going to the negative direction, that means I'm going to subtract 360 from 65. So I'm going to go 65 and then the negative way around to get back to that point. And then I end up with -295. And I don't need to do a second time because that will be outside my -360 range. So these are all the answers or solutions for when theta is 65 degrees. But also remember we have another theta, which is 115. And I do the exact same thing as I go around the circle by adding 360 once and then adding 360 twice. And these are also part of my solutions. And then since I need to go to the negative direction, I add a -1 times 360 and I get -245. And so these are my solutions as well. So now I have every single solution between negative 360 degrees and 10,080 degrees, which is nice. And these are all the solutions. But what if I don't, what if they say just from negative infinity to infinity, how do I come up with something? Well, we don't have all day to list all those solutions from negative infinity to negative infinity. So what we do is we come up with an expression. And the expression is based off of the expression that we use to calculate the other ones. 65 plus anything whole number times 360 will give me a solution. And 115 plus any whole number times 360 will give me the solution for thetas that look like 115. And so then that looks like an algebraic expression of this, where n can be 0 or a positive or negative whole numbers, okay? And we call that the integers. So this is my solution for when the degrees can be from negative infinity to positive infinity, okay? Last but not least, we're talking about reference angles, and we've used them, we just haven't referred to them. Is what angle does the point make with the x-axis? And so in this case, alpha can be represented in 4 different reference angles with the x-axis. And in this case, this is alpha in the first quadrant, alpha in the second quadrant, alpha in the third quadrant, and alpha in the fourth quadrant. They all have the same reference angle of alpha, but they do have different degrees. This is some value between 0 and 90. This is some value between 90 and 180. This is some value between 180 and 270. And this is some value between 270 and 360. Oops, I have to do that wrong. 260. And that's if I'm going in the positive direction. If I'm going in the negative direction, this is some value between negative 270 and 360, and vice versa. Okay? So that's just wanted to let you know about those reference angles as well. Okay, that's it.